Okay, in relation to problem 8, this goes back to the comparison of two lines. For example, if we get these two lines and these two lines, then the top as a percent of the bottom here looks to be about 60%, or 0.6 if we want to do it as a ratio. The bottom, or in here, the top is a proportion of the bottom would be, the top is about 150% of the bottom in length, which is a ratio of about 1.5. Now, if we independently do these, do the bottom as percent of the top, this looks like maybe 170% of this, and this looks like maybe 70% of this. So if I take 60%, 170%, put it on a graph, well, 60 would be here, 170 would be about here. That would give us a point about here on the graph. Okay? Now, and similarly with 150, 70. 150 out here, 70 here, gives us a point about here. The point would be on or near the curve we have on this graph. Now, we were given on the problem a graph with a bunch of points. Now, I've got the points in red. Okay, they have been kind of obscured by the orange that I put on top of it, but you can pretty much see where each point is in red. And what you're asked to do is estimate the deviation of each point from the curve. Okay, the deviation is the vertical distance between the point and the curve. So vertical is measured in the up and down direction. This point is 0.15 above the curve if we use the green scale. And let me back up a second. The first question was actually, the graph was given in the white scale, 100, 400. Of course, you got 200, 300 in between. And the same here. If we, and those are percents. Okay, those would be that would be the scale if we use the percents as a basis for constructing the graph. We could have equally well used the ratios, the 0.6, the 1.5, and so forth, and we would have had ratios of 1 corresponding to 100%, 2, 3, 4 corresponding to 400%, and the same here. So the green scale is the ratio scale, the white scale is the percent scale. On the green scale, this would be 0.15. If we wanted to do it on the white scale, the percent scale, that would be 15%, correspond to 15% discrepancy between the point and the curve. Again, I chose the green scale. These are all relatively small deviations compared to even this one, but much less these two. For example, this point lies this far above the curve, and that distance is about 1.2 on the green scale. Okay, this distance here from this point up to the curve appears to be about 0.8. I didn't do a very good job of making that line vertical, so it could be off by quite a bit, and you could as well in making your estimates. But these would be the estimates of the deviations. And what you're asked to do then is find the average squared deviation from the curve for the given points. Well, the deviations are these. I've just written down the numbers that I indicated on the graph. The squared deviations are going to be these. And if you look at these numbers, and actually if you calculate your squared deviations and think about how big they are relative to one another, you find that the squares of all these deviations are much, much smaller than either the squares of these. And in fact, if you added up all the squared deviations of the last 5 points from here on, it's going to be almost insignificant compared to the sum of the squared deviations of the first 2. In any case, the mean of the squared deviations is, we add them up, divide by 7. And if you add them up, you get something around 2.2, and dividing by 7, we get something pretty close to 0.3. I think it probably comes up pretty close to 0.35, give or take a hundredth, but you get the idea. Okay, that's what you were asked to do. And of course, your estimates are likely to have deviated or been significantly different than mine. First place, you have a better graph. I didn't draw this graph perfectly, as we'll see. Okay, well, that's the second question, the mean of the squared deviations. And then I comment that what we're trying to do when we fit a curve is minimize the mean of the squared deviations. So we could ask the question, like, if we move this graph a little bit to the left, that'll make this deviation a little bigger, but it'll make this one a little smaller. Does that help? We also note that these points are really about the only ones that have a significant effect on the squared deviation, and moving left or right is the thing that has the greatest effect. If we move up or down, well, that has an effect also, but these points don't have a whole lot of influence. It's these first couple points that really pretty much determine the mean of the squared deviation. And that has implications for how well this model actually fits the information that we have. Then you're asked to test, do we get a constant y ratio if we double x? So we start with an x value out here, cut that in half, cut that in half, cut that in half, and call those points x1, x2, x3, and x4, those x values. And we use the graph to estimate the corresponding y values, y1 corresponding to x1, y2 to x2, y3 to x3, y4 to x4. And we look at the ratio of the y values. Well, y2 appears to be about 70% of y1, so y2 over y1 is maybe about 0.7. y3 looks more like 60% of y2, at least it does to me, but yeah, those are not too far different. But y4 is maybe 0.3 of y3, so that ratio is not the same as these. So it doesn't appear that we have constant ratios based on the graph that I've sketched here. There's no apparent constant y ratio, and there would be no point in going further with what we do when we have a constant y ratio, which is to get a power function. However, the graph on your test, if you did that, your y ratios for doublings of x would be pretty close to 0.5, and they would be pretty consistent. Now, you might have gotten 0.4 or 0.6, but 0.5 is probably the best ratio that you would get off of the graph on the test. Now, y equals ax to the p is your general power function, and when you have a constant y ratio for doubling of x, that's what you expect. Then, in that case, and you can refer back to the solution on problem 1 of the exam if you want more detail on how this works out. So I'm not going to go into as much detail, but this means that y2 over y1 would be equal to x2 over x1 to the p, where y1 is the value that goes with x1, y2 is the value that goes with x2. Now, the ratio x2 over x1 for these points is always 2. If the y ratio is always 0.5, we conclude that 0.5 equals 2 to the p. And then if you understand the laws of exponents and think about it a little bit, for if this was the correct ratio, we'd have 2 to the negative 1 being 1/2, which is 0.5, so that p would be negative 1. Now, if you got 0.4 or 0.6, you'd either have to use logarithms or trial and error to determine a reasonable value for p. But for the graph as it is, negative 1 is a reasonable value. And that value of p would lead us to the model y equals ax to the p, which would be ax to the negative 1, since p is negative 1. In that case, if y is 100 when x is 100, and that appears to be pretty consistent with the graph as I drew it, then you would have 100 equals a times 100 to the negative 1, and if you solve that, you get a equals 10,000, which would imply the function y equals 10,000 over x. That would be the power function for this curve. And if you use the green labeling, then y equals 1 when x equals 1. 1 here gives you 1 here. And a is 1. If you run through the process, I didn't run through the details, you plug in 1 and 1 into this In this case, you get a equals 1, so you get y equals 1 times x to the negative 1, or y equals 1 over x. You could pick points on your graph and test them against whichever model, whichever scale you use. If you use the green scale, you would use this model. If you use the white scale, you would use this model. Comment also that the best fit for the data on the test is y equals 8558x to the negative 0.978. Compare 8558 to the 10,000. Compare negative 0.978 to the negative 1 power that we have here.